with some overview. I want to say that wave functions are generally important to consider when studying quantum mechanics and in general quantum systems. And indeed, evidence suggests that we live in a quantum universe, a universe that expanded rapidly many billions of years ago during an era we call inflation, and is also currently expanding at an accelerating rate. And for these reasons, I think it's well motivated and interesting to study wave functions in models of expanding universes. And specifically, what I want to discuss today is how to find the wave function, how to perturbatively solve the Schrödinger equation in order to find the wave function for a specific theory in a specific context, which is going to be interacting massless scalar fields in a fixed de Sitter background, and I'm going to go into that and explain what that is. And the method we're going to be using is I'm going to show you how you can solve the Schrödinger equation perturbatively by computing a Euclidean path integral in Euclidean anti-de Sitter space. And our ultimate goal in this line of research is to hopefully find a useful tool to study the late time behavior of a wave function in a model of an expanding universe. All right, so the way I plan to proceed is to first talk about what wave functions are. I want to briefly introduce these concepts, some of the concepts I'll be discussing to the general audience that may not have a strong physics background. Then I want to motivate why we consider computing the wave function in de Sitter space specifically, and I'll talk a little bit about what de Sitter space is. And finally, I'm going to show you how you can compute the wave function. And in this final part, we're going to be computing Euclidean path integrals in various examples to make sure we understand how this can be done. And at the end, I plan to discuss some of the results that we find. All right, so firstly, what are wave functions and why do we want to solve the Schrödinger equation? So wave functions are, as I said, important when studying quantum mechanics. And as the name suggests, they're functions, mathematical functions, which when squared tell us something about the probability of observing a given outcome in an experiment. So for example, if I'm performing an experiment to locate the position of a particle, and the wave function squared looks something like this, then this tells me that that in my experiment there's a low probability of observing the particle to be in this region over here, and a higher probability of observing the particle to be in this region over here. So you can understand why the wave function is important as it relates to the probability distribution of outcomes of experiments.